Okay, so part two, we are going to cover Hardy-Weinberg equilibrium. And in general, allele frequencies and genotype frequencies can be completely independent from each other. But in certain conditions that are somewhat common in real life, we can predict the genotype frequencies using allele frequencies. So this is in the case of infinitely large populations or populations that are approaching infinitely large populations, if they're randomly mating, and then there's also no evolutionary forces like genetic drift or migration. So first I want to talk about what we mean by allele frequency and genotype frequency being independent from each other. So let's say it's half and half. So half of the alleles are big A and half of the alleles are little a. So if we look at the genotypes frequencies, there's 3 genotypes that you can have. And in one population, you could have something like this. So 50% of the population is homozygous for big A and 50% is homozygous for little a, and none of the population is heterozygote. So in this case, you would have, again, 50% big A and 50% little a, and I leave it to you to kind of try to confirm that. You can also have something like this, where 10% is homozygous, 80% is heterozygous, and then 10% is the other allele that's homozygous. And so this, again, would also match the allele frequencies of 0.5 and 0.5. So you, in general, can't always assume you know what the genotype frequency is if you're given the allele frequency. And the opposite is not true. If you're given the genotype frequency, you can always calculate the allele frequency from that. So what we're talking about is if these 3 conditions hold, so if you just randomly select an individual from the population to mate with the other and kind of do that, what is the genotype frequency based upon that? And so that's what Hardy-Weinberg tells you. And so the idea of that is that you just simply use a Punnett square in order to calculate this. So we're going to follow the approach that I've talked about. So you randomly choose a mother and you randomly choose a father, and you indicate the 2 alleles that they can produce. So the mother could either produce big A or little a, and the father can either produce big A or little a. And so if we look at the entire population, the probability that it's big A is simply equal to p, little p, which is the frequency of the allele in the population. And then the other would be q. And then the same would be true for the male. And so in order to do, you simply do the Punnett square. And so if we looked at the probability of this genotype, it's simply p squared. Little a is simply q squared. And then there's 2 genotypes that would be identical. That would be pq. And so if you sum those up, it's equal to 2pq. So this is kind of an easy way to rederive Hardy-Weinberg equilibrium, but it is right here. It's the equilibrium is summed up right here. So the frequency of big A is equal to p squared. The heterozygote is 2pq, and little a is q squared. So this is something that you should memorize. You're going to need to know it for the test, for example. And so again, if you sum up the allele frequencies, it's equal to 1. And so this is just simply another way to show if you sum up the genotype frequencies, it is also equal to 1. So this is what Hardy-Weinberg equilibrium means. And so if we did it for this particular case, if you had 50-50, that means the big A would be 0.25. So 0.5 squared is 0.25. 2pq is equal to 0.5. And then q squared would be also equal to 0.25. And so if the population was in Hardy-Weinberg equilibrium, it would have to have these genotype frequencies right here. So these 2 populations would not be in Hardy-Weinberg equilibrium, and one of these things must be violated. So for example, random mating could be violated. So in this situation right here, if big A's only mate with big A's and little A's only mate with little A's, then you violated this random mating assumption, but this is how you could get this genotype frequency right here, for example. Or if there's some sort of evolutionary force, maybe the heterozygotes are at an advantage, so the homozygotes end up dying much more likely. are much more likely to die, then you end up having more heterozygotes than homozygotes. All right, so an example of using Hardy-Weinberg. So this is an example, I believe, from the text, looking at an allele called the CCR5 delta 32 allele that is in the CCR5 gene. And the CCR5 gene encodes a receptor for strains of HIV-1, and so the HIV-1 uses this receptor in order to enter into a cell, replicate, and then produce a bunch more viral particles. So this allele was identified because people ended up being resistant to HIV infection. So they based upon kind of their behavior of having sexual relations with individuals that were HIV positive, but they never actually became infected with HIV. And so this allele was actually identified and shown to be protective against HIV infection. So if you're homozygous, you're resistant, and then heterozygotes are susceptible to infection but progress more slowly to AIDS. And so this delta 32 is a deletion of 32 base pairs. And so you can identify this in an approach called PCR followed by restriction enzyme digest. So we're going to cover this more in the Torres section of the class of kind of how you do that. But this also is kind of a practical application. You know, at the beginning we talked about the CRISPR-Cas9 babies that were created in China. I'm not sure if created is the right word, but the babies that had CRISPR-Cas9 genome editing, and these babies were engineered to contain this allele. So by engineering them contain homozygous alleles, because they were born to parents that had HIV, they would be resistant to the HIV infection. It was kind of the ethical justification of why this should have been done. So individuals that are heterozygote look like this, individuals that are homozygote look like this, and then homozygous for the other allele look like this. And so this is just the size of the DNA, and so you can see the size of this DNA is approximately 32 base pairs different. So 403 minus 371, and so that's where the name delta 32 comes from. So this is a example of genotyping individuals. So here we have genotyped 100 individuals for this allele right here. So only 1 out of the 100 is homozygous, so only 1 out of 100 is protective. So this is actually a rare allele, so most people are not protected against HIV. 20 are heterozygote, so they're partially protected, and then 79 are not protected at all. And so again, this was done just by using this approach in order to look at each individual to figure out what alleles they're carrying. So if we wanted to calculate allele frequency, we can do that. So we are not using Hardy-Weinberg yet. So on this whole slide, we're not using Hardy-Weinberg. But right now, all we are doing is calculating the allele frequency using the genotype frequencies. So if we calculate P, so this is this allele right here. So these individuals each carry 2. So there's 158 alleles within these individuals. There's 20 within the heterozygotes, and then there's 0 within the homozygotes, delta 32. And so if we add all these up, there's 178 of the one allele. We can do the same approach for the delta 32, and so there's 22 delta 32 alleles within the population. So if we sum these up, that's equal to 200. So little p in this situation would be 178 divided by 200, so that's 0.89, and then Q would be 22 divided by 200, was equal to 0.11. So that is one approach that you can use to calculate the allele frequencies based upon genotype frequencies. This approach is pretty similar. You just calculate the genotype frequencies explicitly, 0.79, 0.2, and 0.01. These all add up to 1. And then you can simply do 0.79 times plus 1/2 times 0.2 plus 0 times 0.01 to calculate this. I think this is a little bit clearer how to do it, but because the textbook covered it, I also included this in the slide. All right, so we haven't used Hardy-Weinberg yet, but now what we're going to do is use Hardy-Weinberg to see if this population seems to be in Hardy-Weinberg equilibrium. And so P is equal to this, Q is equal to this. So if we calculate the expected genotype frequencies, we simply do the P squared, 2PQ, and Q squared. And so this right here is equal to these three numbers. So these are the expected genotype frequencies, and then these are the actual genotype frequencies right here. So 0.79, 0.2, and 0.01. So you can see that this example actually matches pretty well, and you would do something like chi-squared if you wanted to actually determine are they statistically the same or statistically different from each other. So this here is an example of using Hardy-Weinberg to calculate your expected genotype frequencies, and we found that this population is pretty close to Hardy-Weinberg equilibrium. You can also do Hardy-Weinberg for 3 different alleles. So an example of this is blood type. So we've seen that there's 3 different alleles for your blood type, an A, a B, and a little I. And so you can extend this to include 3 alleles. And so this is pretty straightforward. So now you have P, Q, and R, and P, Q, and R sum up to 1. So you have to, the probability of these alleles has to sum up to 1, but now we just added this extra allele frequency right here, which we call R. So if we want to do Hardy-Weinberg for this, again, we simply use the Punnett square approach. So an individual randomly, a female randomly pulled from the population has a P probability of doing the A1 gamete, Q of the A2, and R of the A3. And so we fill out this entire square, we group the similar genotypes to each other, and so what you end up having is P squared, Q squared, R squared are the probabilities of the homozygotes, and then 2PQ is the probability of the heterozygotes. So now let's do a real life example of this using blood type, and there are again 1, 2, 3, 4, 5, 6 different genotypes that you can have, and so this corresponds to the 1, 2, 3, 4, 5, 6. So, this would be, IA, so the probability of being that would be P squared. This would be IB, and then this would be little I. So, and then these would be the heterozygotes. So PQ would be IAIB, PR would be IA little I, and QR would be IB little I. So this, the genotype, and this just shows, exactly the genotype frequency, just this is the same as this. So here we have shown you the allele frequencies of these 3 alleles in a population, so 0.38, 0.11, 0.51. And if we calculate P squared, we find it's 0.14 for this genotype, 0.39 for this genotype, and then both of these have the same phenotype, so the phenotypic frequency is 0.53. B, you can do the same thing using Q squared and 2QR, so the expected frequency is this. AB, the expected is this, and then the expected for O is this. So again, this all comes from the fact that, alleles are not all equally common in a population, but they have their own allele frequency, which means the probability of being the A blood type is not the same as your probability of being a B blood type, and so forth. All right, so one final example of using Hardy-Weinberg in a practical situation. So now we are going to have a situation where we have a phenotype, cystic fibrosis, that we know is autosomal recessive. And so we know that the incidence of cystic fibrosis is approximately 1 out of 2,600 people of Northern European ancestry. So in this population, the frequency of the phenotype is 1 in 2,600. And so this means the frequency of this genotype is little c, little c. But now I asked you the question is how common are carriers? So you might want to know how common carriers are in the population. And so how do you do that? So you either do that by genotyping and knowing the genotype and having like some sort of approach like this where you can genotype individuals, but in general that's often not the case, especially from like 15 to 20 years ago. And so you can use Hardy-Weinberg to calculate the carrier frequency. So if we assume that this population is in Hardy-Weinberg, then we can use this right here to calculate the carrier frequency. So we can calculate Q squared using this information right here. So the probability of being cystic fibrosis is 0.0004, and so you can use that to calculate Q is equal to 0.02. Now you can calculate P by using the relationship that P plus Q equals 1, and so little p has to equal 0.98. And now we can calculate the carrier frequency being 2pq. So the carrier frequency is approximately 4%. So approximately 4% of the population are carriers for cystic fibrosis. So you actually have a reasonable chance of being a carrier for cystic fibrosis, but you only will have kids if you kind of both you both are carriers together. All right, so this is Hardy-Weinberg and a few examples to kind of take you through how we use it.